So chapter 10, we focused on gases and gas laws. After phases of matter, we spent a whole chapter on gases themselves because of the unique properties they have. Just the fact that they occupy the space of their container and the shape of their container, and the volume and shape can be so easily influenced, is really the reason why we study gases unto themselves in a separate chapter. We started with the KMT, or kinetic molecular theory, for ideal gases. Remember, we made the distinction between an ideal versus a real gas. An ideal gas is hypothetical. We fix the game for ourselves so that when we're talking about gases and we are performing calculations, that we can ignore some of the stuff that's sort of negligible about a gas to make the calculations much more simplistic, but understand that an ideal gas is purely hypothetical. Ideal gases do not actually exist, although there are certain gases under certain conditions that will behave more or less ideally. So the KMT has four important components. One is that gas particles move in constant random straight line motion. Gas experiences elastic collisions, or the gas particles experience elastic collisions, meaning that energy can be transferred from one particle to another but not gained or lost. Gas particles are so small compared to their distances that their own size is negligible. So something like a big old molecule like sulfur hexafluoride versus H2, which is a tiny molecule, in an ideal scenario, those sizes, or the size difference between those two gases, would be negligible. And four, gas particles have no attractive forces or no intermolecular forces. They do. They're very weak, but what we're saying here is they're so weak that we can consider them to be negligible for an ideal gas. We also introduced temperature scales, so we looked at Fahrenheit and Celsius, then we looked at the conversion and really the derivation of what is the third scale we looked at, which was the Kelvin scale. And we need the Kelvin scale for a couple of reasons. One, the Kelvin scale is a scale that has no negative temperature value. So 0 on the Kelvin scale actually means something. 0 on the Kelvin scale means there is no more energy to be had in the substance. We call that absolute zero, where all molecular motion stops. The other reason why the Kelvin scale was necessary is because it is the only temperature scale that is directly proportional to gas volume and gas pressure, which allows us to set up proportions, which makes, again, the math just that much easier. So you should be able to convert in and out of those temperature scales. Then we're just going to go through the gas laws that we looked at. The first gas law that we looked at was Charles's law. Charles's law was looking at the relationship between gas volume and temperature. So volume and Kelvin temperature are directly proportional. They are linked by a proportionality constant that we get by taking the volume and dividing it by temperature, or vice versa, just knowing that in any mathematical relationship that is directly proportional, the proportionality constant can be found by dividing the two variables into each other. Graphically, we get a linear relationship between volume and temperature. We know graphically that it's directly proportional because not only is it linear, but it goes to the point 0, 0. So all directly proportional relationships between variables have to be linear, but also go through the origin. In addition to knowing the formulas, in addition to knowing the relationship between them, it's important to be able to justify why the relationship exists. So remember, in this case, if pressure is constant, right, which is the assumption here, and the number of moles are constant, we're not changing any of those things yet, then the volume is coming from how far apart the particles are or how close together they are. Temperature is going to affect that because if we increase the temperature, the particles are going to have more energy. They're going to be able to move faster and further away from each other, and as long as they're in a flexible container, they can. They will start to move further apart, and if the particles are further apart, that corresponds to a volume increase. If we decrease the temperature and take some energy away, the particles move slower and are able to move closer together. Particles moving closer together correspond to a volume decrease. So that's the first relationship we looked at there. The next gas law that we looked at was Boyle's law. Boyle's law is looking at the indirect or inverse relationship between pressure and volume. We get a hyperbolic graph, as shown there, right, asymptotic to both the x and y axis. Here temperature is constant and moles of gas are constant. The relationship with this one's a little weird because we can look at the pressure either inside or outside of the container, right? Those things should be the same. but the relationship is that if the volume of gas is increased, the pressure is going to decrease, and if the volume of gas is decreased, the pressure is going to increase, right? Indirect means they go opposite each other. Their change is opposite. How we justify it when we talked about pressure, gas pressure specifically, is based on the number of, or the frequency of collisions the gas particles are making in a container or around a container. So if I increase the frequency of collisions or decrease the frequency of collisions, that will either increase or decrease the pressure respectively. So in the image here, if we decrease the volume, now I have the same number of particles with the same average kinetic energy, just moving in a smaller space. So the frequency of collisions, meaning like how often they collide with the container walls, is going to increase if they're occupying less space, and that's going to correspond to a pressure increase. Now, we can also say, what if we increase the pressure on the outside of the container? Right? Well, that's essentially what you're doing when you're decreasing the volume. If you take a balloon and you decrease the volume, you're pushing in the balloon. Well, that pressure is coming from you. So increasing the pressure on the outside decreases the volume, which then in turn increases the pressure on the inside, right? Until this pressure on the outside and pressure on the inside are the same. So with this one, it's a little weird because we can actually look at the pressure either on the outside of the container or the inside. And again, this has to be a flexible container. The third gas law we looked at was Gay-Lussac's law. Gay-Lussac's law is looking at the relationship of gas pressure and temperature. So again, it's Kelvin temperature that's directly proportional to pressure. We have a relationship and a graph that looks very much like Charles's law. The justification here, this gas law has to be observed in a rigid container, meaning the volume cannot move, it can't expand or contract. If we think back to Charles's law, if we increase the temperature, the gas particles have more energy and will start to move faster, and they will want to move further away from each other. And in a flexible container, they can, but in a rigid container, they cannot. So instead of increasing volume, their increased energy causes them to make more frequent and more forceful collisions. That's going to correspond to an increase in pressure. And then opposite if we decrease the temperature and take some energy away. We looked at how all of those could be combined into the combined gas law for situations where we have pressure, temperature, and volume changing. Still in this one, the number of moles is constant. But then we looked at Avogadro's law, where the number of moles was changing. And this law is saying at constant temperature and constant pressure, volume and moles have a direct relationship. That if I increase the number of moles, the volume is going to increase. And if I decrease the number of moles, the volume is going to decrease. This, of course, has to be in a flexible container. But this one should just sort of make sense. You put one breath into a balloon versus 5 breaths. The balloon with 5 breaths, assuming each breath is the same, is going to be larger. We also developed what we call Avogadro's hypothesis here, which says at the same temperature and pressure, equal volumes of gases have equal moles. That's what his law is saying. If the V is the same, then the N is going to be the same. What may not be the same is the mass of gas or the number of atoms, but the number of particles, right, the moles of particles of gas will be the same. In order for a gas to occupy, let's say, 20 liters, there has to be some set number of molecules at a given temperature or pressure to occupy that space. We looked at STP conditions here. STP stands for standard temperature and pressure. Those specific values are 1 atm, or 762 or 760 millimeters of mercury, or 101.3 kilopascals. And then temperature, standard temperature, is 0 Celsius or 273 Kelvin. And in terms of the real versus ideal gases, again, ideal gases are hypothetical. We only ever experience real gases, but we can force the real gases to behave ideally as long as they fit the KMT that we described before. So when will their IMS be the weakest? When the particles are furthest apart. When will their particle size be really negligible? When they're the furthest apart. So how do we get the gas particles to be far apart? High temperature and low pressure. So we say that real gases behave like ideal gases, or behave most ideally at high temperature and low pressure, and when the molecules are smaller, when the particles of gas are small, like H2 or helium. We then finished up with the ideal gas law. This we described as an equation of state. This is not where we're changing conditions, right? This is saying at these given conditions, if I know the pressure and volume and temperature, how many moles would I have? Or if I know how many moles and I know the temperature and volume, what will the pressure be? Remember that this gas constant is equal to PV over NT. So it's really like a combination of the combined gas law and Avogadro's law. And that this is 0.0821 liters times atmosphere over mole Kelvin. Remember, we said this is just like pi in math, where pi is relating the diameter and circumference of any circle. This gas constant's relating pressure, volume, moles, and temperature for any gas sample, any ideal gas sample. We looked at using Pivnert for some stoichiometry. Before, if we were dealing with gases and we wanted to find the volume, we were restricted to saying that the gas was at STP, and we could use that 1 mole of gas at STP is 22.4 liters. But what happens when the conditions are not STP, when the temperature is not 0 degrees Celsius, when the pressure is not 1 atm? We can use Pivnert. So we know that stoichiometry is all about moles. We know how to go from grams to moles. If we want to go from moles to liters or liters to moles, Pivnert is going to be what we use to help us there if the conditions are not STP conditions. If they are, you can use the 22.4 liters. But if they're not, we have to plug in and out of Pivnert. But that we practice a lot with how that can help us in those scenarios. The last two gas laws that we looked at were Dalton's law of partial pressure, which essentially says that if I have a sample of different gases, the total pressure in the sample is a summation of the individual, or what we called partial pressures, of all the individual gases. And based on the laws we've looked at before, the partial pressures are basically going to be in ratio or in proportion with how many moles of gas are in that sample. So if I have a sample with 2 moles of gas and 1 mole of gas, the sample with 2 moles is going to be contributing twice as much pressure as the 1 mole will be. The total pressure will be a combination of all of them. We looked at mole fraction. Mole fraction is the moles of one gas over total moles. And we can use that mole fraction to figure out what the partial pressure is or what the total pressure is. If I take the total pressure and I multiply it by whatever the mole fraction is, essentially a percent, I'm going to get the partial pressure for that given gas, right? So the partial pressure is dependent on the fraction it exists in the container by mole. And then the last law we looked at was Graham's law. Graham's law of effusion and diffusion is saying that gases will effuse or diffuse into or out of a container based on their molar mass. And it's an inverse square of the molar masses, meaning the heavier the gas molecule is, the slower it's going to move. And the lighter the gas molecule is, the faster it's going to move. That is the qualitative relationship you should understand. Quantitatively, we can plug in to say, you know, if I know the molar mass of one gas and I know the molar mass of another, then what is their relative rate to each other? So let's take helium and oxygen here. Helium has a mass of 4 and oxygen has a mass of 32. So if we look at just plugging that in, 32 over 4 gets us 8. And then if we take the square root of that, we get 2.82. So what is that saying? That's saying that helium moves at a rate 2.82 times faster than O2 based on their molar masses. Remember, the inverse part, the way we set it up, if we're looking at the rate of one over the other, this is always going to be the lighter gas, the one that's going to move faster. and its molar mass will go down here, where the heavier gas, the molar mass will go here, to keep the ratio greater than 1, for just for basically ease of understanding. So that's all we covered in the gas and gas law chapter in chapter 10, and you should be ready now for your chapter 10 throwback quiz.